In section 4, we're talking about series and sigma notation, and this is part of Algebra 2 State Standard number 22. Students need to find the general term in the terms of arithmetic series and both finite and infinite geometric series. Our objective is to identify series and to use sigma notation. And let's look at our definition for an arithmetic series. That's the sum of the terms of an arithmetic sequence, and a geometric series is the sum of the terms of a geometric sequence. And a series can be written in a shorthand using this letter of the Greek alphabet called sigma, and we call this summation notation, or the summation sign. So instead of writing 2 plus 4 plus 6 plus 8 plus ... plus all the way up to 100, we can write the symbol looking like this. Now, this is the series that begins with the term where n starts with 1 and ends with a value of 50 for n. So there are 50 terms in this series, starting with term 1, going to term 50. And we read this notation as the sum of 2n for the values of n from 1 to 50. The general term, 2n, is called the summand, while n is called the index number. So we're keeping track. We've got our general formula for the terms themselves, and then n is the term number that we're referring to in this series. If we were to expand that series and look at it a little bit more in depth, that means we're going to replace n with 1, replace n with 2, replace n with 3, replace n with 4, all the way up through n including replace n with 50. The first and the last values of the index are called the limits of the summation. So again, in this case, 1 is the lower limit, 50 is the upper limit. If we have an infinite series, we replace this number 50, or whatever the number may be, with the infinity symbol. That represents the upper limit. That tells us the summation is an infinite series and does not end. All right, let's try an example or two. Let's start with taking our series from summation notation and writing it and expanding it to see what it is. So first, we're going to go from j equals 1 to 20, where we have -1 raised to the j power times j plus 2. First step is everywhere we see a j to replace it with 1. So our exponent is 1, and we have j as 1. Next, we want to replace all the j's with 2. Next, we want to replace all the j's with 3, and then eventually, because we're not going to write all 20 terms out, we'll write the last term. We're going to replace j with 20. And so if we do this, 1 plus 2 is 3. -1 to the 1 power is -1 times 3 is -3. Next term, 2 plus 2 is 4. We're going to take that 4, multiply that times the -1 quantity squared. And a -1 times itself is +1 times 4 is +4. And then we've got -1 cubed, which will be -1, times 2 plus 3, which is 5. And last, the negative raised to an even power is positive. So +1 times 20 plus 2, or 22. That would be our expansion of the series. And it looks like we're alternating signs, starting with a negative, and then a positive, and a negative, and a positive, etc., etc., all the way through. So that's expanding the summation notation or writing out the series. We're going to do that again for another example. In this case, it's an infinite series. We're starting out with k starting as 1, going through infinity. And everywhere we see k, the first term we're going to replace it with 1. Second term, we're going to replace k with 2. Third term, we're going to replace k with 3. And we can't write infinity, so we'll just write ... Simplifying that, 1 minus 1 is 0, 2 to the 0 power is what we have there. 2 minus 1 is 2 to the first power, 3 minus 1 is 2 squared, and that will simplify. In the denominator here, anything to the 0 power is 1, so 1 divided by 1 is 1. 2 to the first power is 2, so that's simply 1/2. 2 squared is 4, so that's 1/4. So we have the series 1 plus 1/2 plus 1/4 plus etc., etc. We have an infinite series. What we'd like to do now is to try to go back the other direction and take our series and try to write it in sigma notation. So we have 10 plus 15 plus 20 plus ... plus 100. And a couple ways to do that. One is look at a strategy. We've got multiples of 5. Starting at 10 though, and going to 100. If we factor out the 5s, we could say 10 is 2 times 5, 15 is 3 times 5, 20 is 4 times 5, and 100 is 20 times 5. One way we could write this in sigma notation or summation notation is to let n start with 2 and go through 20. So n doesn't always have to start at 1. It could start at 2, go through 20 in this case. And our formula is 5 times whatever n is. So 5 times 2, 5 times 3, 5 times 4, all the way through and including 5 times 20. That's one approach. Another approach is to find the common difference in this arithmetic sequence, which is 5. Write the first term, which is 10. Find the nth term. The formula for that, t sub n, is the first term, 10, plus the number of terms minus 1 times the common difference, 5. Distribute out the 5 is 5n minus 5. And 10 plus negative 5 is 5. So we have 5n plus 5 as our formula. But let's factor that 5 out. And what we can say is this. Let's try to find n if the last term is 100. So with our formula, t sub n is 5n plus 5. We're going to try to find how many terms there are. I know we could count, but let's just think that this might be larger on the test. Because, I'm not going to let you count by 5s from 10 to 100. You could figure that out too easily. So for solution 2, we're going to say 100 is 5n plus 5. And if we solve for n, let's subtract 5 from both sides. Divide both sides by 5. There are 19 terms. So our formula could say we're starting from term 1, going through and including term 19, and then the formula is 5 times the term number plus 1 more. So that would be a second way to represent this solution. One way, as we saw just a moment ago, is to start with term 2, go to term 20. 5 times n is that formula. Another approach is saying, well, we start at term 1, but 1 times 5 is 5, not 10. So we want to, for our formula for the nth term, add 1 to the index number k here. So that's going to be from 1 to 19, 5 times k plus 1. All right, let's try another one. Let's try another series that we're going to go backwards into sigma notation. And in this case, I think this is fairly clear. The numerator is always 5. We're alternating our signs from addition, subtraction, addition, subtraction. And our denominators look like 2, 4, 6, 8. That should be fairly simple. So, and it's dot, dot, dot. So we're going to start with term 1, n equals 1 to infinity. And we're going to raise negative 1 to a power. Now, if our signs alternate, that's what we're going to do, negative 1 to a power. If they alternate positive, negative, as they do in this case, we need to have the odd number terms positive. So we might, if we start with an odd number of term, we're going to have to add 1 to that. If it were the case we started negative, we could just raise that to the n power. So you've got to decide whether the even or the odd terms are the positives or the negatives. So in this case, negative 1 to the n plus 1 power. The numerator is always 5, and in here it's 2 times the term number. So term 1 times 2 is 2, terms 2 times 2 is 4, term 3 times 2 is 6, term 4 times 2 is 8. So that's the formula for the nth term, 5 over 2n. And if we take that negative 1 to the n plus 1 power, that'll alternate our signs, positive, negative, positive, negative. And we're going from term 1 to infinity. That's our look at sigma notation for today's lesson.